Welcome to another spherical moment. This video is more of an introduction to graph theory. Some basic notions, such as walks, trails, and paths will be discussed. A graph G consists of a vertex set V and an edge set E. The elements of V are called vertices and represented by dots, while the elements of E are called edges and represented by lines. Sometimes we write VG and EG for clarity, especially when there are several graphs. For example, this is a graph with its vertex set and edge set listed. The way we read graphs is similar to how we read train maps. Each vertex represents a city, and if two vertices are joined by an edge, it means that one could travel between the two cities directly via train without going through another city. A UV walk W in G is a sequence of vertices in G beginning with U and ending at V, such that consecutive vertices in the sequence are adjacent. That is, W starts with U equals to V0 and continues with V1, V2 to Vk equals to V, where k is non-negative, and Vi plus 1 is an edge for I equals to 0, 1 to k minus 1. The walk W is said to have length k. For example, the walk W1, phi 3, 1, 4, 3, 2 is a phi 2 walk of length 5. It seems that the walk W1 contains some unnecessary detour. Hence, the notion of a trail and a path are introduced to aid discussion of some such redundancy in walks. A UV trail is a UV walk in which all edges are distinct. A UV path is a UV walk in which all vertices are distinct. Let's go through some examples to familiarize ourselves with these notions. The following are examples of a phi 2 walk. We shall determine which of them are trails or paths. W1, phi 3, 1, 4, 3, 2 is a trail since all edges are distinct, but not a path since the vertex 3 is repeated. W2, 5, 3, 1, 3, 2 is not a trail since the edge 1, 3 is repeated, and not a path since the vertex 3 is repeated. W3, 5, 3, 1, 2 is a trail and a path since all edges and vertices are distinct. W4, 5, 3, 2 is a trail and a path since all edges and vertices are distinct. Let us make some observations from this example. A UV path is not necessarily a shortest UV walk. W3 is a 5-2 path but not the shortest 5-2 walk. Two vertices U and V may not have a unique shortest path. W4 and W5, 5, 1, 2 are both shortest 5-2 paths. W1 is a 5-2 trail but not a 5-2 path. Generally, does there exist UV path that is not a UV trail? Why or why not? The next theorem says the converse of the first observation is true. A shortest UV walk is necessary an UV path. We state this formally. If a graph G contains a UV walk of length k, then G contains a UV path of length at most k. Can you figure out a proof? The proof. Since G contains an UV walk, let P, starting with U equals to V0, V1 to Vk equals to V, be a shortest UV walk. We shall show that P is a UV path. Suppose for a contradiction that P has repeated vertices, say Vi equals to Vj for some I strictly less than j, where Ij is between 0 and k. Then we can remove the vertices Vi plus 1, Vi plus 2 all the way to Vj from the path P to obtain a shorter UV walk, namely U equals to V0, V1, all the way to Vi, which is equals to Vj, and continues with Vj plus 1, Vj plus 2, all the way to Vk, which is equals to V. This contradicts the minimality of P. Clearly, the length of P is at most k. This completes the proof. I hope you enjoyed the video. Please share, like and subscribe for the latest video. Leave in comments any problems or topics you are interested in. Alternatively, you may email me. Thank you for watching.